So hello everyone, welcome back to us for education. Today we'll be solving the chemistry paper 34 predicted paper for the May June 2025 session. So I've taken these questions from CrackALevel's worksheet that was published on their website. I've only included the redox titration question and the enthalpy change question. So we'll be only solving the question 1 and the question 2. I'll not be solving the question 3 because it is purely based on the observations of the salts. So therefore I do not have any salts here. So now we'll only be solving question 1 and question 2 which I predict to come. Let's begin. So question 1 says Fe1 is an iron salt in which all the iron is present as Fe2 plus cations. You will work out the percentage of iron in the salt by titrating a solution of this salt with a standard solution aqueous potassium magnate. 7. Fe1 is unknown iron salt, Fe2 is the 1 mole per dm sulfuric acid, and Fe3 is 0.01 mole per dm potassium magnate. So first of all they are asking us to weigh out the salt. So weigh the tube containing Fe1, which is the salt, tip the contents of the tube into 250 cm cube beaker, reweigh the empty tube, and record all your readings in a suitable form in the space below. So we have taken the readings, mass of the empty beaker plus lid, which is 100 grams, and mass of the beaker plus Fe1. So you have to include the 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 decimal places to show the precision of the instrument. And mass of the Fe1 used will be the beaker minus the Fa1, uh, Fa1 plus beaker minus the beaker mass. So preparing the solution. So to the salt in the beaker, use a marine cylinder to add approximately 200 cm cube of Fa2 and stir until all salt has been dissolved. So what are we actually doing is that we are dissolving the salt into 200 cm cube of you can say we are adding 200 cm cube of Fa2. So what was Fa2? Fa2 was sulfuric acid. So pour the contents of the beaker carefully into 250 cm cube graduated volumetric flask until the small funnel. Using the small funnel, rinse the contents of the beaker twice and little distilled water and add these washings to graduated flask. Fill the graduated flask to the line with distilled water and shake carefully to ensure adequate mixing. So fill the burette with 200 with Fa3, pipette 25 cm cube of solution of Fa1 from the graduated flask into the conical flask. So we are taking actually 25 cm cube of solution of Fa1 from the graduated flask. Okay, so into the conical flask titration, titrate the solution of Fa1 in the conical flask with Fa3 until the first appearance of permanent pink color. You should perform a rough titration. So in the space below record your bullet readings. So we have taken these reading initial, final and volume used. So the rough titer here will be 23.90 cm cube. To show the precision we have to use is 90. Carry out as many accurate titrations as you think are necessary to obtain the consistent result. Make certain any recorded results show the precision of your practical work. Record in an appropriate form below all the bullet readings and the volume Fa3 added in each accurate titration. So we have taken these results. I already showed you how you have to make the table, but you can also include the best titer column at the end. This table is actually made horizontally, but we can also make it vertically as I showed you in the revision guide. And also one point to note here that you have to keep the other result which is non-concordant as 23.50, and you can say it should have more than 0.1 cm cube difference. From your accurate titration, obtain a suitable value for the to be used in your calculation. Show clearly how you have obtained this value. So we have taken the concordant results and divided by 2. So it will come as 23.15 cm cube of Fa3. So Fa3 was actually came in a 4. Okay. Now show your working and appropriate to an appropriate significant figures in the final answer to each step of your calculations. Calculate how many moles of MnA4 were present in the volume of Fa3 calculated in B. So we calculated the moles as moles of the KMnO4, or you can also say Fa3. It will be concentration into volume. So concentration was given as 0.01 and volume was 23.15. But we have to divide this volume by 1000 because it is in cm cube, and we have to convert into dm cube because you are multiplying with mole per dm. Okay, so this will come as, let's just calculate this. So this will be 2.31 into 10 power minus 4. 2.31 in 10 power minus 4. Now use the equation to calculate how many moles of Fa plus 2 were present in the conical flask. So now we can just use the molar ratio. So MnO4 minus 1 and Fa2 plus. So the ratio between these is 5 and 1. When this was 2.31 into 10 power minus 4, this will be x, and you can just cross multiply 5 into 2.31 into 10 power minus 4 and divide by 1. So it will be, let's just calculate this, it will become 1.16 into 10 power minus 3. 1.16 into 10 power minus 3. Now they are telling us calculate number of moles of Fa2 in your weighed sample. Now this is a little bit tricky question, and here's where most of the students actually stuck. So as you know that the solution of the Fa1 that we actually prepared, it was, and the Fa1 which reacted with the Fa3 in the titration, it was just 25 cm cube of the Fa1. Okay, it was 25 cm cube of Fa1. And where did it come from? This came from the 250 cm cube of volumetric flask. Okay, so I hope it's clear. Now what are we going to do is that if the 250 cm cube was made up of the salt, because you know that we dissolve that salt in the 250 cm cube. So what are we going to be doing is that 25 cm cube contained how much? 1.16, we just calculated right now. And so what will 250 cm cube contain? We can find this out by cross multiplying this. So it will come as, let me just calculate, into 250, 1.16 10 power minus 3 into 250, and then divide by 25. So it will come as 1.16 in 10 power minus 2. Okay, so these will be the moles of Fa2 the in the sample. So these will be the moles of Fa2 in the sample. Now we can just do it here. So this will be in 25 cm cube, and in 250 cm cube it will be x. So it will be 1.16 in 10 power minus 2 mole. Okay, this will be the answer of this part. Now let's move on. Calculate the percentage of iron in Fa1. Now how are we going to be doing this part? So we have calculated the moles of Fa plus 2 in the weighed sample, and now we are just going to be finding the percentage of iron in Fa1. Okay, so we have the moles of iron. It was 1.16 into 10 power minus 2. Let's find the mass of it. The mass will be 55.8 into 1.16 into 10 power minus 2. Okay, this is the mass of Fa2 plus mass. Okay, this is its mass. So 55.8 into 1.16 into 10 power minus 2, it will be 0.64728 grams. Now we actually calculated the original mass of the Fa1 in the start, if you remember. This was the original mass. Let me show it to you. This was the original mass. Fa1 used was 2.5 grams. Okay, so now 2.5 grams is the total mass. Okay, total mass is 2.5 grams. Now when we are calculate the percentage iron in Fa1, we are going to be dividing the mass of the iron 0.64728 divided by 2.5 and into 100. So this will give us the percentage. Let's just calculate this quickly, and this will give us 25.89. So you can just round it off to 25.9%. Okay, this will be the answer. Now the D part says there are a number of sources of potential error in this experiment. One of these is uh, involves the readings using the balance. State the maximum individual error in any single balance reading. So now as you know that we took the reading of the balance to two decimal places, which was 100 and 2.50. So the uncertainty in one individual reading is the least count divided by 2. So the least count will be actually 0.01 divided by 2. So it will be 0.005 grams. This is the you can say the uncertainty in individual reading. When we will be taking the reading multiple times, we have to multiply it by that times. Calculate the maximum percentage error in the mass of Fa1 used in your experiment. Now how do we calculate this? So the burette has a reading, but they are telling us about the Fa1. Okay, there is no connection here with the burette. So we took the mass two times, because one time of the beaker, no, sorry, of the container, and second time of the together with the Fa1. So it will be 2 times 0.005. So the uncertainty here will be 0.01. So now how are we going to be calculating the percentage error? Percentage error actually equals to 0.01 and divided by the mass you actually used to calculate it, which was 2.5 of the Fa1, and into 100. So we will be getting the result 0.01 divided by 25 into 100. So it will be 0.4%. So this will be our answer. Now let's move on to another question of the enthalpy change. Okay, you are to determine the enthalpy change of neutralization for a different acid from that used in question 1. So we are not going to be using the sulfuric acid anymore. The acid is represented by Hb, where B minus represents the anion. So it can be anything. Okay, it can be Cl, it can be iodide, it can be bromide. Okay, so Fb3 is 2 mole per dm cube acid Hb. Fb4 is 72 gram per dm cube sodium hydroxide. Read through the method before starting your practical work and prepare a table to show your recording result. Experiment 1 says place the plastic cup in 250 cm cube beaker, pour 25 cm cube of Fb3, which was the NaOH actually, into the large measuring cylinder. Measure and record temperature of Fb3. Rinse and dry the thermometer. Use smaller measuring cylinder to transfer 25 cm cube of Fb4 into plastic cup. Measure and record temperature of Fb4. Add 25 cm cube of Fb3 to Fb4 in the plastic cup and stir the mixture. Measure and record the highest temperature reached. Calculate the record the average initial temperature of the solution and calculate the record temperature rise. Empty the plastic cup, rinse it with water and shake it to remove excess water. Repeat the method given for experiment using 50 cm cube of each solution. So now we are not going to be using 25 cm cube of FB3 or FB4, we are going to be using 50 cm cube of each solution. Okay, use the larger measuring cylinder for FB3 and smaller measuring cylinder for FB4. So this means that we are going to be taking the FB4 still 25 cm cube, but we are going to be taking FB3 as 50. So we have taken these readings. The initial temperature of FB3 is 25 Celsius, and initial temperature of FB4 is also 25 Celsius. The average initial temperature of FB4 plus FB3 is 25. So rise in temperature is 8.0. This is actually the highest temperature of the mixture. Okay, it is actually going to be coming after the highest temperature. Like we are going to be writing the final temperature, which is 33 for both, and then we are going to be making a row for rise in temperature or the temperature change. Show your working and appropriate significant figures in the final answer to step of your calculations. So show by calculation that in experiment 1 the number of moles of acid was in excess of the number of moles of sodium hydroxide. So now how are we going to be doing this? Let's just see. So it was 2 mole per dm cube of the acid, and how much of we were using it? It was 25 cm cube. Okay, and the NaOH was 72 gram per dm cube, and we were using 25 cm cube of that as well. Now let's see. First of all, we are going to be finding the moles of Hb, which was 2 concentration into volume. Okay, 2 into 25, but 25 is divided by 1000 because we are converting it into mole per dm. So 25 divided by 1000 into 2, it will be 0.05. These are the moles of acid. Now let's find out the moles of NaOH. Now you can see that its concentration is given in the form of this 72 gram per dm cube. Now we can just see that the mass of the sodium hydroxide is 23 plus 16 plus 1, so it is actually 55 grams. Let me just calculate it. So NaOH is actually equal to 40 grams. I have written 55 by mistake. So it is actually equal to 40 grams. Now we can just see that how many moles are actually 72 grams. 72 grams is equal to x moles, while 40 is equal to 1. Now let's see that 72 divided by 40, so 1.8 mole. So its concentration will become 1.8 mole per dm, and then the volume divided by 1000, so it will be, let's calculate this, 22 divided by 1000 and into 1.8. So 1.8 into 25 divided by 1000, it will be 0.045. 0.045. So now we have shown that the number of moles of acid are in excess. So 0.05 mole is greater than 0.045 mole of NaOH. So acid is in excess. Now they are telling us to calculate the heat energy evolved in experiment 1. Assume that 4.2 joule of heat energy changes the temperature of 1 cm3 of solution by 1 Celsius. So we know the formula for the heat energy evolved. It is mc delta theta. So we know that the mass is actually of the solution, because they have given us the 1 cm cube is equals to actually 1 gram. This is just an assumption. Okay, so we are going to be seeing that how much of the solution is actually used. So 25 cm cube of FB4 and 25 cm cube of FB3, so it will be 50 grams. This will be 50 grams, and then we are going to be multiplying with the heat capacity. So this is 4.2, and then the delta change was 8. Let's calculate this. 50 into 4.2 into 8. It will be 1680. This will be 1680 joules. Calculate the enthalpy change in kg mole per dm for experiment 1. Now in this part we always use the moles of the limiting reactant, which was NaOH. So what we do is that 1680 joule of energy was released the because of 1.8 mole. Okay, it was because released because of the 1.8 mole of NaOH. So how much will be, as it is mole per dm? Okay, so we are going to be using mole, 1 mole. So how much will be released by 1 mole? Let's just check this out. So x will be equal to 1680 divided by 1.8. This will be 933. This will be 933.3 joule. As the temperature is raised, we are going to be using minus to show the exothermic, and it will become 933 divided by 1000, so it will become 0.9 kilojoule. Okay, then calculate the number of moles of sodium hydroxide neutralized. Neutralized means reacted in experiment 2. So let's check this. So this is actually for the question 1. um, this is for the FB3 and FB4. For this, for the experiment 1 actually. But what are we going to be using is that we are going to be using 50 cm cube of the FB. Let me just check. Repeat the method given for experiment 1 using the 50 cm cube of each solution. Use the larger measuring cylinder for FB3 and the smaller measuring cylinder for FB4. So we'll be still using 25 cm cube of FB4, it means. And but they have written that we are going to be using 50 cm cube of each solution. So let's just assume that we are taking 50 cm cube of FB3 and also 50 cm cube of FB4. So it will be 50 cm cube of FB4, which was the NaOH. Let's just find its moles. So it was 50 divided by 1000, and what was its concentration? Its concentration was 1.8. Let's find its moles. 50 divided by 1000 into 1.8. So it was 0.09. Let's find for the acid. It will be into 2. So acid will be 50 divided by 1000 into 2. It will become 0.1. So let's just write it 0.09, because all of this will be used up because it is the limiting reactant. Okay, calculate the enthalpy change in kg mole per dm for experiment 2. So Q is equals to mc delta T. The mass was 50 plus 50 is equals to 100 grams, and then 4.2, and then the delta change was same. Let's just take it as, you can say, 10. Okay, let's just take this as 10. This will be 10. So 100 into 4.2 into 10 is 4200 joules. Now 4200 joules was caused because of 1.8, which was actually the, you can say, the limiting reactant. So what was for 1 mole? So this will be x joules. X will become 4200 divided by 1.8. This will become 233.3, 233.233 actually 0.3 joules. Now divided by 1000, so this will become 2.3 kilojoule, and this will be minus as the temperature rose. So let's just move on. The accuracy of larger Meyering cylinder is 0.5 cm cube, and the accuracy of smaller Meyering cylinder is 0.25. Calculate the maximum percentage error in the measurement of the volume of FB2, FB3, and the measurement of the volume of FB4 used in experiment 2. So we used 50 cm cube of FB3 with larger measuring cylinder. I told you we always take it twice because we are taking the reading twice. Larger measuring cylinder, so it will be the percentage error will be 0.5 into 2 and then divided by the volume 50 into 100, so this will be 0. This will be 1 divided by 50 and into 100, this will be 2%. For the FB3 it will be 2%. Now let's check it for 50 cm cube of FB4, which actually used the smaller one. So the percentage uncertainty will be 0.25 into 2 divided by the 50 cm cube into 100. This will become 0.25 into 2 and divided by 50 and into 100. So this will be only 1%. So this will be 1%. Now they are telling us suggest a change to the method used in A that would improve the accuracy of your results. So what we can say is that you can place a lid to prevent heat losses, or you can use glass wool insulation. This can also be done. What else can be done is that use a more precise thermometer, and what else you can write. It is only of 1 mark. Okay, the upper part is for 2 marks and the lower is for 1, so they have given the marks together. So precise thermometer, and you can also use pipette to reduce uncertainty, because because volume is only measured once. So these can be the improvements. I have also listed all the improvements in my revision video, so watch it if you have problems in identifying the limitations and improvements. Now this part says this is another question of the Enthalpy change. In this experiment you will use a thermometric method to determine the concentration of a sample of alkali. You will mix varying volumes of acid with a fixed volume of alkali. So this is an important point. We have fixed volume of alkali and measure the temperature rise that occurs. So you will use your experimental data to calculate the enthalpy change for the neutralization of the acid with alkali. FB3 is an aqueous sodium hydroxide and FB4 is 2.2 mole per dm HCl. Support the cup into 50 cm cube of beaker and use thermometer to measure the enthalpy change, the initial temperature. Okay, so let's take it as a room temperature 27.0. You have to include the 0 to show the precision of the thermometer. Thermometer can give you 27 as a whole number or like 27.5. Okay, not like 27.1 or something like that, but 27.5 or 27. Fill a burette with distilled water. Fill the other burette with FB4. So FB4 was the HCl. And for the experiment 1, use the 10 cm cube pipette to transfer 10 cm cube of Fb3 into the cup and add 9 cm cube of distilled water from the butte into the same cup and stir the mixture and use the thermometer to measure the maximum temperature obtained. Record the maximum temperature in the table, empty and shade dry the cup ready for use in experiment 2. So we are adding 9 cm cube of the distilled water here and we are adding only 1 cm cube of Fb4 from the other butte into the same cup and using 10 cm cube to transfer 10 cm cube of Fb3 into the cup. So 10 cm cube of Fb3 plus 9 cm cube of the distilled water, 19 cm cube, and Fb4 is 1, so 20 cm cube in total. So we are going to be recording these results. So what we actually did is that we varied the volume of water 9753164 cm cube and volume of Fb4 was 13579 4 and 6. So we actually kept the the volume of alkali, which was, let me just see, the alkali was Fb3. So we are actually keeping the Fb3 the same. Okay, it will be the same as 10, but we would be varying the Fb4 and the volume of water in a way that it equals to 10 always. So 10 plus 10 is always equal to 20 in the case. So we'll be checking the maximum temperature. So it is 29.5, then 32, then 34, then 33, then 33, and then 34.5, and then it is decreasing 34.0. Carry out two further experiment which will enable you to determine more precisely the volume of before that gives the highest maximum temperature. So we have already included these two values at the 6th and the 7th place. So record your measurement for these two experiments in the table. So plot a graph of maximum temperature reached on the y-axis and the volume of before used. The scale on the y-axis should include a temperature 2 Celsius above the highest maximum. So we have to leave space for 2 Celsius above the highest temperature. For example, if we have the highest temperature here as 34.5, we are going to be leaving the space up to 26.5. So let's just take it to 28 or 27. Now let's check how much boxes we have on the x-axis. It is 1, 2, 3, 4, 5, 6, 7, 8. Now let's check the FB4 range. FB4 is from the highest is 9 and the lowest is 1. So we can just take it to 10. So how many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8. So let me just think that what could we actually do. Can we take it to 10? So yes, we can take it to 10, like 1.25, spacing 1.25, then 2.50, then 2.50 plus 1.25. Do not use the false origin in these type of questions, okay? Because sometimes they ask you to do not use the false origin, and they will likely are going to be asking you to extrapolate the graph to origin. So 5.0 plus 1.25, it will be 6.25, 6.25, then plus 1.25, it will become 7.5, 7.5, then 8.75, and then it will become 10.00. This excess is actually volume of Fb4 used, and its unit is cm cube. Now let's also plot the y-axis. We are going to be taking the range to 34.5, or you can say 2 Celsius above it. So they are actually asking us draw two straight lines of best fit on the graph. One line should should show where the maximum temperature recorded was increasing. The other line should be after the highest temperature. So actually we are going to making the two lines, the increasing and the decreasing. We are going to be showing the trend of increase and decrease. So extrapolate both lines so that they intersect. Use a graph to determine the volume of before that reacts with 10 cm cube of FB3. Okay. So use your graph to determine the volume of FB4 that reacts with 10 cm cube of FB3. So how are we going to be doing that? Because we are just measuring, just taking the volume of FB4 and that maximum temperature. So it is going to be the highest temperature actually, because it will just perfectly react with 10 cm cube of FB3. So now what graduation should we take on the y-axis? Let me just first mark the boxes 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So how much spacing can we take? We can take the spacing of 40. Okay, so 4, we can take the spacing of 4, but we can also include, let me just check, 5 into 10 will be actually equal to 50. It will be more spacing, so let's just take it to 4 space. So 1 unit will actually be equal to 4 Celsius. So this will be 4, this will be 8, this will be 12, then 16, then it will become 20, then 24, then 28, then 32, then 36, and then 40. So we have covered the range, and the units for this will be maximum temperature change. The units will be Celsius. Now let's plot the individual points. So FB4 was 1 at 29.5. It was 1 at 29.5. Let's check where 1 was. So what we could do is that 1 minus 0 divided by 0.125. It will give us 1 divided by 0.125. It is 8 places from the origin. So 29.5 will be above 28. So 29.5 minus 28 divided by 0.4, it will be 3.75, or you can just take it close to the 4 one. So this will be the point. This will be the point. This is our first plot. Let's check the other ones. 3 and 32 and 5 and 34. 3 and 32. So 3 minus 2.5 divided by 0.125. It will be 4 places from the 2.5, and 32. 32 is a perfect plot at the y-axis. So this will be the plot, and 5 and 34. So 34 between 32 and 36, and 5 is this. So this will be the plot here. Then we have 33, 33 and 34.5. So now let's just take this as increasing. and this will be the decreasing. Okay, so we will just amend this results a little bit, like you can say let's just amend it little bit to 33.5, because these are just assumed values. So we can just amend this, take 33.5, because in the paper you will have a perfect trend with the values. So this will be 33 and this will be again 33.0. So now let's take it as next plot is 733, 933. Okay, so 733, 33 is, let me check where 33 is. 33 will be between 34 and 32, so it will be bit at this point. So where is 7? 7.5, so 6, 7 minus 6.25, 7 minus 6.25, 7 minus 6.25 divided by 1.0.125, it will be 6 units from the 6.25 mark, and it will be about this point. Okay, then for the ninth we also have the same value. For the ninth one, let's check. 9 minus 8.75 and 5 divided by 0.125, it will be 2 units from 8.75, 2 units from 8.75, so this will be the point. And then we have 33.5 at, we have 33.5 at 4. Okay, so it is at 4, and at 6 it is 33. So where is 4? Let me just check it again. So let's just maintain the trend, because at 4 it will be a very lower point and it will actually decrease the curve very much. So 34.5 and at 4. So 4 is a bit here and 4 will be here. These values are actually not correct. This will form a very irregular type of trend. So we can just amend it to 9.5 and 10.0. So 9.5 and 10.0. So where is 9.5? 9.5 minus 8.75, 8.75 divided by 0.125. This will be 6 units from 8.75, and the temperature change is 33.5. So we can just look it at here. This is the point here, 1 unit ahead of this. So this will be the point and this will be the last point. This will be the last point. So now we can just make these two lines. Let's make these two lines. So this will be the first line of best fit. We are going to be extrapolating it. Okay, this will be the first line of best fit, and this is going to be the second line of best fit. Okay, so now you can see here clearly that they intersect at about this point. Okay, they are intersecting about this point. So this will be the point at which it reacts with 10 cm cube of Fe3, because when it perfectly neutralizes it, so it will cause a maximum temperature change. So this will be actually the point. Let's interpolate it. So it will give us the value on the x-axis, which is the volume of FB4 needed. So this will be about 5.0125. Okay, so it will be 5.125 and 5.25. So it is 5.25. This will be the answer for this part. Let's move on. Give your answer to see part 2, part 3 and part 5 to appropriate number of significant figures. Calculate the number of mole in hydrochloric acid in the volume of FB4 in B. If you are unable to determine the answer to B, use 4.1 cm cube as the volume of FB4. So let's just calculate the moles of HCl. The moles of HCl will be concentration into the volume. So how much volume did we take? Let's just check. So HCl was FB4, its concentration was 2.2. So we were actually varying the volume of FB4. So this will be actually the volume of FB4. In this will be the volume of FB4 because they are telling us in the that calculate the amount of mole of the hydrochloric acid in the volume of FB4 in part B. So this is the part B, 5.25. So 2.20 into 5.25. So let's calculate this. 2.2 into 5.25 and divide by 1000. It will come as 1.16 into 10 power minus 2. 1.16 10 power minus 2. Actually we are getting 1.155, but we have to maintain three significant figures as they have told us that we have to maintain appropriate significant figures. So we are going to be taking it to three significant figures. So use your answer to see part 2 and the information on page 4 to calculate concentration of in mole per dm of sodium hydroxide in FB3. So how can we calculate the concentration of NaOH? Let's just see. So the concentration, we have not been given the concentration, but we know how much volume are we actually using. So as you know that the HCl and NaOH react in 1:1 molar ratio. What will actually happen is the moles of the HCl will be equal to the moles of NaOH. So it will also have 1.16 10 power minus 2 moles, but in 10 cm cube because we are not varying its volume. So let's calculate the moles. NaOH will be equal to 1.16 into 10 power minus 2 into 10 divided by 1000. So it will be about 1.16 into 10 power minus 4 be 1.155 into 10 power minus 4. So it will be just can say rounded off to three significant figures. Calculate the energy released when the volume of FB4 is neutralized by sodium hydroxide. So show your working. So it is neutralized at the maximum temperature. So what will be the volume at the maximum temperature? The volume of FB4 was 5.25 and the volume of water will be 10 minus 5.25. 10 minus 5.25, it will be 4.75. So together it is actually 10 cm cube, and 10 plus the FB4 it will be actually 20 cm cube, or you can also say 20 grams. So 20 grams into 4.2, and the temperature change was how much? It was the highest temperature change was, let me check it from the graph. It was at this point, and this is about 33.4. So 33.4 minus the initial temperature which was 27.0. Let's take it and calculate this. 20 into 4.2 into 33.4 minus 27, it will come as 537.6, 537.6 joules. So 538 will be rounded off value. So use the answer in C part 2 and C part 4 to calculate enthalpy change of neutralization. So we have to take the moles of the limiting reactant. So 538 is caused by how much? By 1.16 in 10 power minus 4 mole of NaOH, as it is limiting reactant. So how much will be from 1 mole? Let's take this value. It will be about, let me calculate, 538 into 1 divided by 1.16 in 10 power minus 4. So it is actually a very large value. It will be 464 kilojoule. Not kilojoule, it will be just 464 into 10 power 3 joule. Then we have to divide it by 1000. It will be minus because the temperature is rising and it will become as 464 kilojoule. Okay, so the theoretical value of enthalpy change of neutralization is 57.6 kilojoule. So as we are using the assumption values, there there will be more change when we are using the enthalpy change with the calculating it with the assumption values. So calculate the percentage error in your value of enthalpy change from C part 5. Show your working. So the theoretical value is this, and our value is very large because we are just using the you can say the assumption values. But in reality, when you are performing the experiment, your value will be smaller than this. For example, if you are just performing it in the lab, it will come as something about 44.3 kilojoule. Okay, it can never be larger than this theoretical value. Theoretical value is larger than the experimental value. So how do you calculate this error? The error is calculated as, I'll be taking this value. Okay, so it will be 54.3. It will be subtracted from 57.6 and then divided by 57.6 kilojoule. We do not need to include the 1000 in the 10 power 3 for the kilo because we are just multiplying with the and dividing with the, adding and the dividing by the same units. So it will be into 100 then. So 57.6 minus 54.3 divided by 57.6 into 100. So it is 5.73, 5.73% error. This means the value is this much of a difference from the original one. Suggest one modification to procedure used in A part that would give a more accurate value for enthalpy change of neutralization. Do not suggest any modification to apparatus. So any modification means we cannot say that you should use a more accurate, you can say, pipette, or you can say graduated pipette, or like things like that, or you can say that we would use a more precise thermometer. So you do not have to suggest modification to the apparatus. What we can do is use volume of FB4 near nearer to endpoint, or you can say volume of repeat the experiment with FB4 volume of FB4 that gives highest temperature change. Okay, so this will be the answer for this. So this was the paper. I have solved all the paper for question 1 and question 2. So I'm expecting a question from redox titration and a question from enthalpy change. And for the salts, I will be I will try to publish a video so that I can tell you which salts I expect. Mostly I expect the iron salts to come, like the iron chloride, and you can say like carbonate salts, something like you can say it could have you can say some other ions, but I mostly expect the iron ions to come this time. So this was the paper. These were just the assumption values, so cope with this because these were added by someone else. I just changed it so it would meet the trend of our question. So share it with anyone you think it will help, and I'll be meeting you in another video. Till then, goodbye.